Okay, so this first one, these factors that affect the state of the matter, what are the two factors? What are the two most important factors, or what are factors?
Pressure, temperature, and intermolecular forces.
Okay, pressure and temp and intermolecular forces. The other way you could say this intermolecular forces one, you could say this is the actual particular substance that you're talking about. So of these three things, which is the most important? Yeah, the intermolecular force of the particular substance is the most important thing, because I mean, we in this room right now, we have all three states of matter. They're at the same temperature, they're at the same pressure. So then the other factor must be the most important thing. So like the nitrogen in here isn't interacting with itself very well, so it's in the gaseous phase. And the phenolic resin, that's what the top of these lab benches, they're so fundamentally sound with themselves that I can drop anything I want on that. I mean, I can just squirt it down with ethanol and catch it on fire and it doesn't care. You guys had burning magnesium metal. Gets dropped on this, nothing happens to it. And that's over 1,000 degrees. The table just doesn't care. So phenolic resins have such a strong intermolecular force, they pretty much don't care about anything.
Is there a solvent that would...
Sure. Yep, absolutely. A phenol solvent.
Is it polar or non-polar?
It's very non-polar. Yeah.
Are there degrees of non-polarity?
Yeah, absolutely. Certainly. So it's all about how not polar something is, right? So like those nitrogens are incredibly not polar, right? That nitrogen compound, or like a helium, no polarness to it whatsoever. So you can have varying degrees, like a methane molecule isn't polar, but it's got some polar nature to it, very little, but it's got a little bit. Which three intermolecular forces are for covalent molecules?
Dispersion, dipole, dipole, and hydrogen bonding.
Dispersion, dipole, and hydrogen bonding. Oh, we got that backwards though.
Yeah.
This is the strongest, middle, weakest. What are the requirements for these forces? So if I'm talking about a dispersion force, what kind of molecule am I talking about? A nonpolar molecule, right? Nonpolar, the electronegativities are what? Close. Or equal. So I don't have differences in electronegativities because the electronegativity numbers are very similar to each other. How about the dipole-dipole? Polar. And
means that it's electronegativity, it needs to be above 0.5.
yeah. A minor difference in electronegativity. And then the hydrogen bonding.
It needs to have a large
A hydrogen bonded to either a fluorine, an oxygen, or a nitrogen. Those are your requirements. And so this is very polar. No. Why does the neon have a lower boiling point than the argon? Size, so actual radius.
Dispersion effect is more prominent in argon?
Why is that?
There's a lot more.
Smaller, less electrons to disperse. Anything else? No, that's good. So every once in a while somebody says something, I'm like, oh, yeah, I guess that works too. Atomic radius is smaller, so the atom itself, the electrons are more tightly bound to the nucleus. And then when I have more electrons to deal with, then I have more of them to push to another side. So the neon literally only has 10 electrons and the argon has 18. So I could push all 18 to one side, or when I could push all 10 to one side, the 18 is always going to be larger. The polarity of that is always going to be larger. We where do we get on Earth? Where do we get the argon from? You can get yourself some argon gas. Does anybody know where it comes from? Huh?
Is there high up in the atmosphere? Tiny amounts.
How about just in the atmosphere? So you breathe in, you got mostly nitrogen and oxygen, and then the other 1% is water vapor, CO2, and a bunch of other things, and one of those is argon. Argon's actually number 5 on the list of things that are in the atmosphere, but less than 1%. So how could we get it out of the atmosphere?
Take everything else out.
Yeah, take all of it. Take a whole bunch of air, cool it down and compress it, turn it into a liquid, and then separate them based off of their densities. What's the surface area of a molecule have to do with its melting point?
It's like Velcro. If you have little Velcro, it's easy to pull apart. But if you have lots of Velcro, it's harder to pull apart.
Okay, so more
Certain
area to touch. To touch adjacent molecules. So if I'm longer, then I have a large area or surface area to be touching another molecule. If I'm small, then only a small part of my molecule can touch the adjacent atoms or molecules. All right, so shows honey having a very high viscosity number. Honey is mostly composed of fructose, glucose, and water. From the structures below, explain why the viscosity is so high. Say again?
There's a lot of opportunity for hydrogen bonding.
I like that. So, what opportunities do I have for that?
You have a bunch of lone H's all around, and then there's a
Not lone H's.
oh right.
H is attached to O's. So every single one of these hydrogens that I'm circling, tell me about it. They're hydrogen bonds, right? So each one of those is a contact point of positiveness and negativeness. So this hydrogen right here is positive, and this oxygen here is negative, and this is all over this molecule. So if you want to use the Velcro analogy, I got a whole bunch of places to connect. Plus there's some length to this molecule, so there's a lot of surface area. So this molecule here could attach itself to another identical molecule in 4 different places, and those places would be tightly bound because we're talking about an intermolecular force of 2 hydrogen bonds interacting with each other. The water molecule can just fit in between stuff and like help other things bind. So the water molecule could do something like what's the shape actually around this hydrogen here, this hydrogen oxygen? Always, right? It's always bent. Why is it always bent? Lone pairs. So I've got a lone pair of electrons, 2 lone pairs of electrons that are taking a position in my tetrahedral, and then the other 2 positions are held by atoms. So this is always going to be a bent molecule. The connection in this place is going to be bent. So this oxygen, hydrogen, this oxygen is here, but this hydrogen is like over here at an angle. So I could have something like another water molecule, could be like this. Let me do some erasing here. So maybe it looks like this. So we've got this bent shape here, and this bent shape here, and this bent shape here of the water molecule. And so then I have an interaction between this oxygen and this hydrogen, and this hydrogen and this oxygen. And so now I've just glued all three of those pieces together. And the water molecule could do that at many, many different positions. This shape is this single carbon-carbon single bond. It can rotate. So all of these three things can actually rotate over to the other side. And then I can have interaction, interaction, interaction. Or I can throw water molecules in there and have everything get glued up together. So the best answer to this question is what Keenan said immediately, which is a lot of opportunities for hydrogen bonding. What are these things? Sugars, right? So sugars bond well to themselves. Like frosting, right? Like sugar frosting, that kind of stuff. Caramel, taffy. High viscosities on those things.